Good morning, guys. Let's see here. Good news is I found a screen recording software. The funny thing is there's been one on my Mac the whole time, and I didn't know about it. So yeah, cool. So anyways, today my presentation is going to be about penicillin class drugs, and just kind of go over what they're used for, the pharmacokinetics of them in the body, and just kind of like the structural properties, how they work, and how the different drugs in the class are similar and different from each other from a structural perspective. So anyways, up here you'll see is Alexander Fleming, obviously. This is the guy who kind of discovered penicillin in the early 1900s, around I think 1928 maybe. And then up here you'll see is a penicillin pill. And this kind of just shows that it can be taken as a pill or it can be injected intravenously. So some common diseases treated by penicillin are pneumonia, strep throat, scarlet fever, diphtheria, syphilis, gonorrhea, meningitis, tonsillitis, and many others. And many of us already know most of these from past personal experiences. Hopefully not the gonorrhea, syphilis part, but I'm sure with strep throat and maybe tonsillitis or pneumonia. So why are there other penicillin-like drugs when penicillin covers so many things and penicillin is kind of the big miracle drug? Well, the reason why we have different penicillin-like drugs is because of antibiotic resistance. Penicillin has been used so much since its discovery. It was used a lot in World War II for the soldiers, kind of trying to keep them healthy and stuff like that. But by being used so much, a lot of bacteria has become resistant to it, and it is not as effective as anymore. So we have different, types of penicillin that are slightly different, but still do the same thing to kind of combat this resistance. So going over the A, D, M, and E of most penicillin, the absorption is usually from the GI tract into the bloodstream, or like we mentioned earlier, it could be injected intravenously, but either way it goes into the bloodstream, and that is how it is distributed throughout the body in the bloodstream, and it's sent to the areas of infection because it will bind to certain components of bacteria, which we'll talk about that here in a minute. And it is metabolized by either the bacteria or the liver, which is then metabolized into an inactive form, which is then secreted, and this is usually secreted through the kidneys, in the urine, but a very little portion of it is excreted through the bile duct in the GI tract. So, how do penicillin drugs work? The main point of these drugs is to inhibit the bacteria from synthesizing its cell wall properly, and this causes structural failure and eventual lysis of the cell. So, it is mainly used in gram-positive bacterial infections. Penicillin drugs really don't have much effect on gram-negative bacteria. So why gram-positive? I know this isn't a micro class or anything like that, but we'll just touch on this briefly. Over here on the left is a gram-positive bacterial cell wall, and this has a ton of peptidoglycan, which is what makes up their cell wall. Plants use cellulose, fungi use chitin, bacteria use peptidoglycan. So you'll see as a gram-positive it has a ton of it over here, and that's really the biggest component of its cell wall, whereas on the gram-negative over here, this big complicated mess, the peptidoglycan is a pretty small little portion in the middle, and by being in the middle, kind of sandwiched in between these two membranes, it really makes it a lot harder for the penicillin to actually get to the peptidoglycan, which is where it will have its effect at. So looking at the peptidoglycan a little bit more in detail, you'll see down here on the bottom, the peptidoglycan is made up by a bunch of G and M subunits, and these are really just acids, like sugar components kind of bonded together, and what gives peptidoglycan its strength is these cross-links between the M subunits, and these are like the little blue links you'll see here, and they're all over the place. And if you kind of zoom into these links here between one of the M and another M in the two strands that cross each other, It's linked together by a DAP, which is diaminopamelic acid, and it's linked over here to the alanine on another one. And what will happen is penicillin will inhibit this cross-link from occurring, which is, so like whenever you take these blue links away, then it loses a lot of its structural stability, and then the osmotic pressure inside of the bacterial cell will cause it to lyse and kind of blow up, so to say. And then also it prevents it from replicating, so if it doesn't lyse, it will then give our immune system enough time to come in and take over. So penicillin, the structure of penicillin, you'll see that it's kind of complicated, but the biggest thing that penicillin has is beta-lactam ring, which is this four-membered ring that you'll see right here. And the thing that makes different penicillin drugs different is this R group over here that's different for each type of penicillin drug. But the beta-lactam ring, as we know from all chemistry classes, four-membered rings are highly reactive. They're pretty unstable. So what will happen is this mimics the alanine that we remember from the cross bridge. It looks extremely similar to the beta-lactam ring of the penicillin. So what will happen is this will bind to the protein that makes those cross links, because the protein thinks that the penicillin is alanine because it looks exactly the same. So it'll bind to that, and then this beta-lactam ring will break open, and it will change conformation and bind to the protein in a certain way that will inactivate it from synthesizing any of the cross links, and that's what kind of gives it its mechanism. So I would assume over time with antibiotic resistance, the protein, when the protein changes, it doesn't change the functional group because alanine doesn't change. So this will obviously stay the same for all the penicillin drugs, but what's different maybe is the R groups with how they bind. So maybe the protein will have resistance to a certain type of penicillin because the R group doesn't bind in a certain way that will inactivate the protein, so we need different R groups. I didn't really find much on that, but that's what I would assume. So we'll look at a few different penicillin molecules or penicillin drugs and kind of see how they differ and are similar from each other. And there's the beta-lactam ring look like on alanine again. So anyways, ampicillin, you'll see it still has the beta-lactam ring here, obviously, and the R group has this amide and phenyl group attached to it. And I was kind of looking at these, and that's kind of how they get their name, with the amide and phenyl, maybe the AM and the P in ampicillin. Pretty cool. Then we have carbenicillin, which kind of has like a carboxylic acid residue over here, and the benzene ring, which is kind of like the carb and then the ben. But that's the R group attached to that. And then over here with amoxicillin, you kind of have an amide and this benzene ring with the hydroxy group attached to it over here, which you'll see. And then dicloxacillin, which is another one. Still, they all have the beta-lactam ring. And then this kind of has like a dichloro attached to the benzene ring, and then this substituent group right here. And then the last one that we'll look at is oxacillin, which again still has the beta-lactam ring, and then it has that same kind of NO ring with the kind of phenyl ring attached to it right there. But and then let's see, we have a little overview slide here with just the penicillin and D-alanine that it will mimic right here. And then these are all the 5 different penicillins that we talked about. And then the red trapezoids kind of show the beta-lactam ring in all of them. And then the yellow circles just kind of highlight how each one of them is different. And then everything else with these drugs are virtually identical. I mean, they are identical exactly. But yeah, so you can pause this and kind of look at this if you want to for a little bit. But yeah, these are the drugs. And that's kind of how penicillin works in the body. Its function and structural differences between its kind of sister drugs, so to say. But anyways, thank you guys for listening to me. We'll catch you next time, and have a good weekend. Or if this is on Monday, have a good week right before spring break. Take it easy.